Today our theorem is bounded linear functionals. So bounded linear functional means if we are having a functional defined on a inner product space, it is said to be linear if we are having f of alpha x plus beta y equal to alpha f of x plus beta f of y, and is said to be bounded if we are having mod of f of x is less than or equal to c into norm x. Now here the statement of the theorem is, let x be a normed linear space and x not equal to 0 be an element of x, then there exists a bounded linear functional f bar on x such that f bar of x not equal to norm x naught and f norm of f bar equal to 1. Means here we are having a normed space, means there exists a bounded linear functional and whose norm will be 1, and generally the value of this functional will be equal to norm of x naught. This we have to prove. So to prove this, we will consider one subspace. That is, let x be a normed space as given x not equal to 0 be an element of x. Now suppose z be an subset of x. Suppose it is containing the elements of the form say alpha x naught, where alpha is any scalar. Now here this z is a subspace we will prove. To prove that any subset is subspace, that is z is subset of x, means if I take x comma y belongs to z, alpha x plus beta y also belongs to z, means I can say that z is a subspace. So we will prove that. Suppose there are two scalars, say alpha 1 and alpha, again another two scalars beta 1 and beta 2. See, these scalars alpha 1 and alpha we will use in the definition of the set, whereas beta 1, beta 2 we will consider scalars along with the vectors x and y. So consider beta 1x plus beta 1y, where x is say alpha x naught, y is say alpha 1 x naught. Then we can write beta 1 alpha x naught plus beta 2 alpha 1 x naught. So beta 1 alpha plus beta 2 alpha 1 x naught is common. Suppose sum of scalar, if we take, we know that sum of scalar is again a scalar only, let that scalar be gamma. So gamma x naught is similar to alpha x naught, means this gamma x naught belongs to z, means it is a subspace. Then on this subspace z, we take one functional say f. We define a functional f on the subspace z as f of x equal to x, meaning will be alpha x naught, as every element in z is alpha x naught form, can be defined as say alpha into norm x naught. Now using this functional, here we can prove that there exists a extension and we can prove the theorem. So as we are having a functional here, first thing we need to prove that it is linear. So we consider f of x plus y equal to f of alpha x naught plus beta x naught. Assume that x is alpha x naught, y is beta x naught. Then sum will be alpha plus beta x naught. Here alpha plus beta is scalar taken outside by the definition of functional norm x naught. Again, if norm x naught is multiplied within the bracket by distributive property, we can write alpha x naught plus beta x naught, that is f of x plus f of y. It implies f is linear. Now also f is bounded. So how it is bounded we will see. If we take mod of f of x, mod of f of x will be mod of f of alpha x naught. Alpha is scalar taken outside, mod alpha into norm x naught. This is of the form mod f of x is less than or equal to c into norm x. Instead of less it is equal, that's why it is bounded function. So when there is a normed space along with a subspace with a linear bounded functional, there exists a extension f bar. This we have studied in Hahn-Banach theorem. So f bar is an extension of f from z to x, means f is defined on z, so f bar is x. So from Z functional f to x functional f bar we are extending such that norm of both will be same. Now we know that norm of this functional will be supremum of mod f of x, where norm x equal to 1 means same thing norm f equal to 1. Now by this we can say that extension f bar of x naught is equal to f of x naught. Here f of x naught can be written as 1 into x naught. So f of alpha x naught will be alpha into norm x naught. So it is written as norm x naught, which is the proof of the theorem. So hence the proof. Now next we will see next topic. Next topic we are having is adjoint operator. Adjoint operator is defined on dual spaces. That is, if suppose x is a normed space, then on x we can define functionals. So there can be defined number of functionals. If we collect those functionals as one set such that each functional is a bounded linear functional, then such a set is called as a here dual space. Dual space is nothing but it is a collection of all bounded linear functionals, which is also a vector space. Means it itself is also a vector space, then it is called as a dual space. Now we will come to the actual definition. Adjoint operator. Suppose x and y be normed spaces. Let T be a bounded linear operator from the normed space x to y. See here it is a operator and here we were talking about the functional. Now here T is a linear operator. Then adjoint operator of T is defined as a mapping from y dash to x dash denoted by T cross. Here the adjoint operator on these normed spaces we are defining it as T cross, where it is defined on T cross is defined on y dash to x dash. Y dash and x dash are dual spaces on x and y. Then this is said to be adjoint operator if it is defined as T cross of G equal to F, where G belongs to y dash, F belongs to x dash. Or we can also say that T cross of G of x equal to F of x. Again f of x can be written as f of x means f will be the functional from x to r, it will be again can be written as g of t of x. So why it is written as g of t of x means when we are having t from x to y, when x belongs to x means we say that tx belongs to y. Then we say that t of tx belongs to y dash. So hence here g of t of x we can write. So a operator is adjoint operator if it can be defined as T cross of G equal to F. Now here, when we are having a adjoint operator, if T is bounded linear operator, then adjoint operator is also bounded linear, as well as norm of adjoint operator and norm of a linear operator both are same. So this completes this topic. Remaining we will see in the next class.